Alright team, so today's lesson, exercise 9L9M, you're focusing on limits, continuity, and differentiability. The main two key concepts are simply continuity versus differentiability. In a way, we've kind of touched on it in the last session when I did the VCE, VCAR question, if you had an attempt with it. Some of the questions you had were related to continuity and differentiability. In order to do them, you first need to understand limits. Now, we did do a bit of limits early on in the chapter. So here are some limit properties in case you're not yet familiar, and some examples that you can work with. One of the, first things to sort of note is that when you're working out for the limit here, say if x was approaching -1 as an example, one of the ways that you've been working with is you substitute x as -1, right? But one of the key problems that you get when you get these limit problems is that you may end up with 0. If you get a 0, it's undefined, so hence you then cannot find the value or what the limit approaches to. So some of the limit problems gets you to practice factorizing, seeing if you can simplify the problem so that you can find a limit. So an example in this case, if it was approaching -1, and I sub -1 in, it's not going to work, so this approach doesn't work. So what we do is we then say, well, limit of x approach -1. Let's see if I can factorize and simplify so that the denominator does not have that x plus 1. Well, simplifying the numerator, that is what, x plus 1 times x plus 1? Yes, that's true. Divided by, and that's x plus 1 in the denominator. Conveniently, x plus 1 divided by x plus 1 is 1. And then you can say, as the limit of x approaches -1, so as x gets closer and closer to -1, what would x plus 1 approach to? So in this sense, you can then say, well, if this is getting closer and closer and closer to -1, let's say it is just almost exactly the value of -1, well then you can say it would approach towards 0. Unlike the top one, we would have had undefined. So if you're not familiar with limit problems, there are some questions as you're going through that get you to practice factorizing them and finding different ways to avoid that problem of an undefined area. Okay? So those are the properties that you can work with. That's the limits. But what I want to talk about today is not so much about how to work with limits, but more about what is continuity and what is differentiability. You need to know it so that you can justify if a point is differentiable or not. Okay? So to do that, can you flip over to the next page? Let's look at continuity first, because differentiability relies on the fact that it needs to be continuous to begin with. Let's have a look. Formal definition of continuity. So what is the definition of continuity? How do you say that a function is continuous? Well, a function is considered continuous at every single point, or at a particular point, so at x equals a, if two conditions are met. Here are your two conditions. One, that the function is defined at x equals a. What does that mean? It just means that when you have at the point x equals a, does f of a exist? Meaning, does it have a y value? Okay, because if there's a y value, that means there's a point. If there's a point, well then, that's the first bit. That's the first condition. The point has to exist, right? So part number one, what does it mean? If you substitute x equals a into the function, will it have a y value, is what we're saying. Okay, so a point actually exists. Condition number two. Condition number two says the limit. So even if you did have a point, it did have a y value, but does the limit of the function as x approaches that value, that a value, does it actually approach the same y value? Okay, so in other words, what I'm saying here is if I approach the x value from both left and right direction, does the graph tend towards the same y value as condition 1? So in condition 1, we said, does the point even exist to begin with at x equals a? Does the y value even exist? Okay, so do they have a y value? And we're like, yes, it has a point. Great. But for it to be continuous, the second condition must exist too, meaning if I approach from the left of the function and from the right of the function towards that x value, is it the same y value? And if it's not the same y value, well then that means the point or the limit does not exist. The example, if you turn back to the first page, this picture here, this is called a piecewise function or a hybrid function. If I asked you at x equals -1, does a point exist? Well, then you'd say, yes, there is a point. Clearly, at -1, I've got 4.5. Right? So yes, there is a y value, so condition 1 is met. Condition 1 ticked off. Yes, f of a does exist. But just because the point exists, it doesn't mean that the function is continuous. We can tell by looking at the graph it's discontinuous, it's disjointed, right? So the second condition is then to check, well, okay, if I approach the function from the left to get to x equals -1, because that's what we were looking at x equals -1, what does the value tend to? And we can see that the limit from the left, it's approaching a y value of -1. So from the left, so how you would write it is you'd say limit of x approach -1 for the function, so f of x, okay? But in this case, I'm approaching -1 from the left-hand side, so I'm going to put a negative just on that side. So say I'm approaching from the left. What does it tend to? Well, it's tending towards -1 based on the graph. I can see that the y value is tending towards -1. Then you check, well, what about if I tested limit of x approach -1, but from the right? Which I use a little positive sign to say I'm approaching it from the right. So if I approach it from the right, so I'm coming from the right, and I'm coming closer to -1, well, the graph is telling me I'm tending towards the value of 4.5. These two are not the same. That means the limit already doesn't exist. Because which one is it? Is the function at that point, is it meant to actually be equal to -1, or is it meant to be 4.5? We can clearly see condition 1 says that it's 4.5, but when I apply the limit does not exist. And the second condition says that you need the limit of x approach a to be the same as f of a. So we need it to be 4.5, but it's not 4.5 on both ends. So that's why it doesn't meet condition 2, and you say it's not continuous. Okay, that's the formal definition. So if you were to prove it in an exam and you had to define, if they said, justify your response why it's not a continuous function at x equals -1, these are the conditions you have to start writing through. Okay, the informal definition is much easier. So if you flick back to the page on continuity, the informal definition is this. In a nutshell, if you had to understand what continuity is, this is the informal definition. A function is continuous if you can draw the entire graph without lifting your pen. So in a visual aspect, if you can draw this graph without lifting your pen off the page, then it's continuous. But you can't write that in the exam. Okay, so here I can do all that, but then I have to lift my pen up to do that little dot and then continue on. That is not continuous. I would draw this and then I have to lift up my pen to continue on and then lift up my pen. Not continuous. I have to draw and then, okay, that's stuck. I have to draw, lift up my pen, and then continue. All of that is not continuous. Okay, but you can't say that in the exam, so you have to learn how to use the first two conditions, which in a logical sense, it makes sense. If you have a y value, great, but then from left and right, meaning does the function reach the same point? Because if it's continuous, it should all follow the same points from left and right and at every single point on the graph, right? So that's the definition of continuity. So far, so good? Okay, so two conditions, that's what you need to remember. Once it is continuous, then you can then look at the next step. Okay, so exercise 9L, 9M, you're practicing to, articulate mathematically whether it's continuous or not. Okay. At the first stage, I guess you can just learn to look at a graph, and really, if you can draw the graph without lifting your pen, it's continuous. Cool. So that already answers part of something later when you're doing differentiability. You can quickly tell which points are differentiable and which points aren't. Yeah. Now, let's quickly look at this graph here. Example 3. Give values of x at which discontinuity occurs and give reasons. Okay, so now we can look at this graph, and I want you to tell me, where is it discontinuous, and give me a reason. So I've drawn it out for you. Usually you don't get this graph. You actually have to draw the piecewise function, but I've done it for you to save you time. Where is it discontinuous? Yes, Rango. At x equals 0. So we've got x equals 0. And is that it? Okay. Again, informal definition. Can you draw this graph without lifting your pen? Well, no. I have to lift my pen off at x equals 0. So that's discontinuous right at that point. And then from up here onwards, I can draw the graph entirely without lifting my pen. So in an informal definition, yes, it is discontinuous at x equals 0, not at x equals -1, because at x equals -1, yes, condition 1, it is met. F of -1 does exist. And then if you did the limits, both from left and right, you'll see that it still tends to the exact same y value for condition 2. That's why at x equals -1, it is continuous, even though it looks a bit funny there. Yes, pretty clearly connected. What was the reason for, when they say give reasons, what would you say as your reason as to why it is discontinuous at x equals to 0? What's the reason? It's only 2 conditions, so you have to be able to identify which condition.
As the limit approaches 0 to left, like it's not equal to the limit approaching 0 from the right.
Beautiful. If you were to prove it, if they asked you to actually justify it, you would actually have to say from left it approaches whatever value, and then limit of x approach 0 from the right. What value? In our case, approaching from the left, what is the value tending towards if I'm approaching from the left-hand side, Noah? What's the function approaching to? 0. Whereas if I'm approaching from the right, what is it approaching to, Tara? 1. Very good. So from the right-hand side, we're approaching the value of 1. So hence, limit does not exist. Or at least condition 2, limit of x approach 0 for f of x does not equal to f of 0. Okay? And hence, or therefore, or hence, at x equals 0, it is not continuous. So far, so good? That's the first exercise. Okay, so the exercise is to get you writing and articulate yourself as to why and how you know it is not continuous. Differentiability is going to be very similar. It's going to be based on the fact that you know how to find continuity first, and then you do a second bit. Okay? All right, so that's the example of continuity. Let's do the last bit, and then that's it for chapter 9. So you've learned so far how to differentiate. You've learned all the techniques from chain rule to product rule to quotient rule to power rule to all the transcendental functions, to then doing derivative graphs. And then now on the last bit is continuity and discontinuity. That's chapter 9. Okay, so everything you need to know about differentiability or differentiation. Next chapter, chapter 10, is applications of it. So how do you apply it? How do you solve things? So we go, let's flip over. Last page, differentiability. So if they ask you, how do you know if a point is differentiable or not? Usually the way that teachers normally teach you as a shortcut, if you didn't understand it at all, they say that it is not differentiable when you have 1, sharp points, or like cusp. And number 2, endpoints. Okay, so if what I say today doesn't make sense to you, that little top corner there will allow you to figure out if it's differentiable or not, but it is not going to be your way to justify if it's differentiable if it comes up in the exam. But you can use it as a reasoning, so you can say at sharp points it is not differentiable. It's just that it's not a way of justifying. It's just one of you, as you're writing and you're saying not differentiable at this point, therefore you carry on. But if they ask you to justify why, if it's differentiable or not, you must learn how to use those conditions. Okay? So, differentiability, 2 conditions. Number 1, it needs to be continuous. So that means you had to know if a graph was continuous or not. So it had to be connected, or you can draw the graph without lifting your pen. So it needs to be continuous at every single point, or at that particular point. And the second one, which is easier to remember as well, if you remember continuity, then the second one means if you want to test differentiability, then the gradient for the limit from left and right has to also be the same. Okay, so continuous was checking the y value is the same for the limit, then differentiability is gradient is the same for left and right at that point. Okay, so here we go. Function can be drawn without lifting your pen. That's what condition number 1 really means. Is it continuous? Number 2, if I approach the x value from both left and right, is the gradient the same? That's it. Does a limit exist for the gradient as well at that particular point? Yeah? So, here we go. If a function is differentiable, then it is continuous. But just because it's continuous does not mean it is differentiable. Okay, just because it is continuous does not mean it is differentiable. And like this first example, that is an example of a continuous function, but it is not going to be differentiable, which goes back to that point where I said a lot of teachers will teach you and say, at sharp points or cusp, you will not have a differential point there. Here's the first example. Let's have a look. Number 1, condition 1, can you draw this graph without lifting your pen, which is the informal definition, is it continuous? Yes, I can draw this graph without lifting my pen. So condition 1's met. Yes, it is continuous. Number 2 though, number 2 is asking, is the gradient as I'm approaching that particular value, so in this case here, looks like the question is at x equals 0, as I'm approaching that, is the gradient from the left, if I'm approaching from the left and I'm approaching from the right, is the gradient the same? So here, limit of x approach, in this case 0, for f dash of x, does it exist? Does it exist? So here we go, let's test it. If I'm approaching from the left side, what is the gradient on the left approaching at x equals 0? 0, because this is clearly all zeros here. 0, 0 at every single point. So I would assume that at x equals 0, it is approaching m equals 0 from the left. So from the left, limit of x approach 0 from the left for the derivative or the gradient is approaching 0. Then I check from the right. That's all right. Well, what about the limit of x approach 0 from the right? What's the gradient tending towards? Not the y values, check the gradients. What's the gradient in this case here? Some constant, but we know it's positive or negative, right? So what's this case? Positive or negative? It's positive, clearly not 0. Okay, so whatever this is, it's all positive gradient, so we can say it is a positive constant. Hence, limit does not exist. And if the limit doesn't exist, condition 2 is not met. That means at x equals 0, so therefore at x equals 0, it is not differentiable. And then just basically, when you say it's not differentiable, you just say that I don't know what the gradient is. That's what it means. Because truly, I do not know. Is it 0 or is it some positive value? What's the gradient? And because I don't know, that's why I don't know what it is. Hence, there's no derivative for it. Yeah? Because when we do the derivative, we're finding the gradient at a particular point. So if I don't know what the gradient is, then of course it's undefined. Yeah? So that's what it actually means. Yeah.
Would you still graph that? Like, would you just two lines, like one at 0 and one at 2 with like open circles.
Beautiful. That's exactly it. So if we were to draw the derivative graph for this from exercise 9D, then we would say that there's a 0 gradient from the x-axis being negative infinity up until 0. And then the rest, well, I don't know what kind of gradient it is, but let's just say it's gradient of 1. Then it would look like this, but you have an open circle at each end because at x equals 0, it's not differentiable. So this is your derivative graph as x goes on. Okay, and then if they ask you to justify, then what I just did on the bottom there, that's what you would go through. So you'd say it is continuous, yes, but the derivative or the gradient does not exist at that point. So hence, that's why they normally say at sharp points. Why sharp points? Because sharp points means it's linear. And if it's linear, when two linear lines connect, and they're not exactly the same gradient, like the second one's the same gradient throughout, then of course, this one will be differentiable on every single point. But when you have a sharp point, that means there's two different gradients. And that's why at the conjunction, or where they connect, that point, I actually don't know what the gradient is. Is it the negative, or is it the positive? Is it the 0, or we don't know. That's why it's undefined at that point. That's why that first definition that's given to most students makes sense, right? So second one, without saying, we can tell that it's actually continuous. Yes, I can draw the graph without lifting my pen. And yes, the gradient is actually the same for all single points. So hence, it is differentiable at every single value or across the domain of this graph. Whereas the third one, condition 1, is this continuous? Yes, it is. I can draw the graph without lifting my pen. So condition 1's met. Yes, it is continuous. And you just got to check now, number 2, does the gradient exist at every single point? Now, there is one point in question. Which point am I looking at? X equals 0. This is the point. At x equals 0, that's the only question we're getting. But you can clearly already see, even though it wasn't linear, you can see that the gradients on the left-hand side, it's positive. Whilst if I'm approaching from the right-hand side, gradient's negative. So just by that inference, as I'm approaching close to 0 from either side, one's positive, one's negative. That means the limit as the gradient, the limit of the function or the gradient, it clearly does not exist because one's negative, one's positive. It's not going to be the same. Okay, so hence, this is not differentiable at x equals to 0. And this explains with all the endpoints. If you drew a graph with different endpoints, that also tells you why. One, it's discontinuous already, but also 2, the gradients will be different. That's why there's 2 conditions will tell you if it's differentiable or not. Yes, Rango?
If there was a function that was discontinuous but had the same gradients, how would you graph it? What would you do?
Well, the part that is discontinuous, the fact that it's discontinuous to begin with, that means it's not differentiable at any point. That is, wherever it's discontinuous, at that point there will not be a differentiable point. Yeah, that's about it, yeah. All right, team. If you like to have a go, you can have a go with the last example yourself to see if it's continuous and does the limit exist, but pretty sure at this point now you should be able to tell if it exists or not. But that's just it. That's what L9L and 9M is, working on limits, continuity versus differentiability. Hopefully now, if you look back at that exam question I gave to you last session for 9D, makes a lot more sense to where you put the open circle for differentiability. Okay? All right, team, I'm going to stop the